Now that we have a general understanding of the Chatelier's principle, that a system at equilibrium will respond to some disturbance at their equilibrium by trying to minimize that disturbance. We looked at adding and removing reactants and products. Now we're going to look at some other things that we can change that will disturb the equilibrium of a system. The first one we'll look at is changing the volume of a container. The end result of this is actually looking at a change in pressure, but there are two ways to change the pressure of a container: adding another substance to the mixture or changing the volume. We're only worried about the gas-phase substances when we look at changing the volume of a container, because those are the only species that are affected by an increase or decrease in pressure. Solids and liquids will not change their properties as we change the volume or change the pressure. When I look at an increase in volume, what we have is those gas molecules will expand to fill that volume, and as a result, the pressure inside that container will decrease. If I have a decrease in pressure, what is going to happen to the reaction is that I'm going to favor the side that has an increased number of moles. I need to compensate for that lost pressure by doing something that will cause an increase in the pressure. It's just the opposite. And so what I look at is my reactant side has 3 moles of gas. My product side has only 1 mole of gas. And so if I can increase the amount of reactants present, what I'm going to see is I'm going to compensate for that decrease in pressure by making more moles of gas that will counteract that decrease with an increase in pressure. So when we have an increase in volume and we see a decrease in pressure, the reaction will favor the side with more moles of gas. For this example, it's favoring the left side. However, it's going to depend on the specific parameters of your reaction. The opposite is also true. If I decrease the volume, I increase the pressure. I increase the number of molecules in a particular space, and so we have an increase in pressure, and now the system needs to respond to minimize that increase in pressure, and it's going to do that by decreasing the pressure. And the way that happens is I go from 3 moles of gas to 1 mole of gas. And so when we see a decrease in volume, it's going to favor the side that has fewer moles of gas. We do, however, have to watch for reactions that have a mixed phase. We still can look at favoring the side with more moles of gas or the side with fewer moles of gas, depending on what change we apply, but we do need to be careful when we look at a reaction. In this reaction, 2 magnesium plus oxygen yielding 2 MgO, what we have here is just 1 mole of gas on the left side of the reaction, and we have no moles of gas on the right side of the reaction. We can still apply our same arguments, but we have to look at just the moles of gas, not the moles of every single substance present in the balanced reaction. So here we look at an example. We have our methanol, our hydrogen, and our carbon monoxide. We have a system at equilibrium. We decrease the volume by lowering the piston. We're forcing these molecules into a smaller space, so we're increasing the pressure. And as a result, we need to do something to reestablish equilibrium that will lead to a decrease in the pressure, because we need to counteract that disturbance to the system. And the thing that will counteract that increase in pressure will be to take some of our reactants and form more products, because we're favoring the side that has fewer moles of gas. If we increase our volume, again, we have our system at equilibrium, we increase the volume, and what we are doing is lowering the pressure of the system, because we have the same number of molecules but in a much larger space, so we'll see a lower pressure. In order to establish equilibrium, we need to have some response to that disturbance of increasing the volume that will counteract that increase and that lower pressure. So what we're going to do is we want to increase the pressure, so we need to take some of our products and decompose them into CO and H2, because that's going to lead to the formation of more moles of gas. And therefore we will counteract that increase in volume, which lowered the pressure, by producing more moles of gas, which results in an increase in pressure. Now, if I change the pressure by the addition of an inert gas, I'm still changing the total pressure of the system, but what I find is that I'm not changing the partial pressure of any of my substances. Therefore, changing the pressure through the addition of an inert gas will not have any effect on the equilibrium of this system. One thing we have to worry about is what is an inert gas? We frequently see that helium and nitrogen are used in inert gases. However, we do have to use nitrogen with caution as an inert gas because it cannot either be a reactant or a product in our overall reaction. For example, I wouldn't want to try to use hydrogen as an inert gas for this reaction because I already have hydrogen. And what I'm really adding is one of my reactants, not adding an inert or unreactive gas. We do not see any shifting of the reaction towards formation of more reactants or more products with the addition of an inert gas because the partial pressures of each gas don't change, just the total pressure does. And remember, when I'm looking at equilibrium constants, Kp values, where P stands for pressure, I'm looking at the pressure of methanol, pressure of CO, and pressure of H2 squared. Since there's nothing in that equilibrium expression about the inert gas because it's not part of the overall reaction, I don't need to worry about it at all, and what I'm going to see is that my equilibrium is not disturbed by the addition of an inert gas. So let's look at an example here. If I have a reaction at equilibrium, we add our N2 molecules to this. And what we see is that our N2 molecules are still present at the end. But we also see that once our equilibrium is here, that we're not really reestablishing equilibrium. We've just taken the exact same thing we had initially, and after we added the N2, the number of molecules of CH3OH remains the same, the number of molecules of H2 and of CO all remain the same. So we have no effect on the equilibrium through the addition of an inert gas. Now we need to look at the effect of changing the temperature. Before we can do that, we do have to figure out, do we have an exothermic reaction or an endothermic reaction? Now, when I look at the first reaction here, I see a delta H value of minus 90.5 kilojoules. What that tells me is that this is in fact an exothermic reaction. The negative sign indicates that heat is being lost from the system. And so what we can actually do is treat heat like a product because heat is coming off of the system. If I look at an endothermic reaction, such as I have down here, what I see is my delta H value is positive. That's how I know it's an endothermic reaction. But what I can also figure out is that heat must be behaving as a reactant because I have to put heat in to get this reaction to proceed. So when we look at a change of temperature for an exothermic reaction and an endothermic reaction, we have to further subdivide this down. What if I increase the temperature of an exothermic reaction? What if I decrease the temperature? What if I increase the temperature of an endothermic reaction? What if I decrease the temperature? And we have to worry about all four of those scenarios. So let's first look at what happens when we take an exothermic reaction. This is where we have heat as a product, so we write heat on the product side. And what happens when we increase the temperature? Well, if I have some reaction, and we'll just write a generic reaction here, A plus B going to C plus heat, because heat is a product here. If I increase the temperature, what I'm really doing is I'm adding heat. And what did we learn earlier? If I add a product, what I'm going to see is that the reaction is going to shift away from that towards the formation of more reactants. So for an increase in temperature of an exothermic reaction, we end up with favoring the reactant. So some of that C will decompose into A and B, and we'll counteract that increase in temperature by using up some of that heat to drive this reaction to the left, to shift this reaction towards the left side. The opposite is true if I decrease the temperature. If I lower the temperature, what I'm really doing is I'm removing heat. And when I remove heat, the reaction is going to need to respond in order to counteract that change. So heat is a product. I remove heat. My reaction is going to shift towards the right, towards the formation of more C. So in this case, it's favoring the products. And this is true for all exothermic reactions. If we increase the temperature, we'll favor the reactants. If we decrease the temperature, we'll favor the products. So that helps us with the exothermic reactions. But now we need to look at the endothermic reactions, and in this case, we treat heat as a reactant. So let's say we have the reaction D plus E plus heat. Remember, I'm looking at an endothermic reaction, so heat is being consumed by the reaction. It's treated as a reactant, and we go to forming F. Now what I can look at is the same thing I looked at for exothermic, increase and decreasing temperature. How does the system respond? Remember that I said if we're increasing the temperature, we're adding heat again. And if I add heat to an endothermic process, what I see happening is if I'm adding heat, the reaction is going to shift towards the formation of more products, in this case F. And it does this because heat is now a reactant, and if I'm adding heat, it's just like adding any other of my reactants. So we see the formation of more product, of more F, we see the decrease in the amount of D and E, but we've minimized that increase in heat that we experience by the increase in temperature. We can also look at the opposite. We can decrease the temperature of the system, and so when we decrease the temperature, what we're looking at is removing heat. So we remove heat from the system, and so what's happening here then is we're losing heat, and so now the reaction is going to have to shift to the left to compensate for some of that lost heat. So when we have an endothermic reaction in which we decrease the temperature, we favor the formation of more reactants. So let's look at an example of this. Here we have our hydrogen, our carbon monoxide, and our methanol. We add heat. Notice that the number of reactants on the products on the left panel is equal to the number of reactants and products in the middle panel. We're adding heat to this. This is our disturbance to our equilibrium, and we need to figure out what's going to happen relative to Le Chatelier's principle. I see that I'm dealing with an exothermic reaction because it has a negative value, and whenever I see that, I'm going to go ahead and write in plus heat, just as a reminder that heat is behaving like a product. So if I add heat, what's going to happen? Well, the reaction is going to shift towards the left. We need to compensate for some of that additional heat that has been added to the heat that is already present in the reaction from our delta H of reaction. And so I see heat is being treated as a product, so if I add product, I'm going to shift my reaction to the left. And this is what we see here. I've lost a methanol molecule, and I've increased the number of CO molecules and the number of H2 molecules. If I look at lowering the temperature or removing heat from the system, I can still start with my same system at chemical equilibrium. I'm cooling the reaction vessel, so I'm disturbing the equilibrium. Notice that at this point in panel 2, we still have all of the same number of each species as we did in panel 1. But now we've removed heat by decreasing the temperature, so the system has to respond to that change. Our delta H, same reaction we were looking at before, is still exothermic. And so since it's exothermic, we treat heat as a product. Now, when I look at this, I say, well, if I'm decreasing the temperature, I'm actually removing heat by decreasing the temperature. And as a result, I'm going to shift this reaction to the right. And so what I see is I actually get the formation of an additional methanol. I've lost a carbon monoxide, and I've lost 2 of my hydrogen molecules to form that new CH3OH molecule. If we looked at endothermic reactions, what we'd see is exactly the opposite. Because in those reactions, remember, it's endothermic, heat is going into the system, therefore heat is being consumed and heat is treated as a reactant. In this reaction, we're looking at the temperature dependence of a complex ion equilibria. We have a hydrated cobalt salt, and we're going to take advantage of Le Chatelier's principle. We're going to put it in a heated water bath and put it in ice and see how it changes colors. So as we have here now, we have a test tube that was in the ice bath, and we have a test tube that was in the hot water bath that looks purple, and we have our control that was left at room temperature. This is an endothermic reaction, so as we put heat into the system, we drive this reaction to the right and we get to the cobalt chloride ion. As we put it in the ice bath, we drive the reaction more towards the left side, and so we have the hydrated cobalt ion present. So now we can go back through these disturbances that affect equilibrium. We can change the concentration of a reactant and see how that affects it. and that can be either increasing the amount of a reactant or decreasing the amount of a reactant. We can change the concentration of a product, again, either increasing or decreasing. We can change the pressure, and we can do that in two ways. One of which is changing the volume of a container, which will have an effect on the shift in the equilibrium, or we can add an inert gas. It will also increase the pressure, or we can remove an inert gas that's already there, and will decrease the pressure. But this has no effect on the equilibrium because what we're looking at is the fact that we're only worried about the partial pressures of each of the component gases. And last, we can look at changing temperature, and we have to look how it happens if we increase or decrease temperature, and whether we're dealing with an endo or exothermic system. Now let's look at an example. PCl5 decomposes according to the endothermic process shown. Which one of the following includes only changes that will favor the decomposition process? When we look at Le Chatelier's principle, we see that there are many factors which affect which way the reaction will shift in response to that disturbance in equilibrium. Before we get started in looking at these changes, we want to first look at the information given in the problem, and we see that the reaction is endothermic, which means delta H is greater than 0, it's a positive value, and that means energy is being put into the system, which means heat is behaving as a reactant. So now we have heat plus PCl5 in the gas phase is in equilibrium with PCl3 in the gas phase plus Cl2 also in the gas phase. So the first thing we want to look at is what happens when I add or remove one of my reactants or products. For part A, I see I'm adding PCl5, and if I add PCl5, it's going to drive the reaction to the right because it's going to respond to that disturbance in equilibrium of too much PCl5 by trying to use some of that, and it's going to favor the decomposition process. The addition of Cl2 will do just the opposite. When we add a product, we now have too much product, the reaction is going to shift in order to accommodate that extra and actually will drive this reaction to the left. The removal of Cl2 will drive the reaction to the right because now we're missing some Cl2, so we'll drive that to the right for both C and D. And then for E, if we add PCl3, we're adding a product, we're going to drive the reaction to the left just as when we added the Cl2. Now we can look at the change in temperature. We determined that the reaction was endothermic because it was given in the problem. We see that heat is going to be behaving as a reactant, and as a result, we look at what will happen if I add or remove heat. Well, if I decrease the temperature, I'm actually removing heat from the system, and so it looks like I'm removing a reactant, and when I remove a reactant, I drive the reaction to the left. So for any time I'm decreasing the temperature, I'm going to drive the reaction towards the left side. Conversely, if I increase the temperature, it's like adding heat to the system, so if I add heat, I'm going to drive the reaction to the right. Just as when I added PCl5, my other reactant, I drove the reaction to the right. Now we have to look at how changes in volume affect the equilibrium. One thing we need to note is that when we decrease the volume, so if we see a decrease in volume, we see an increase in pressure. And when that happens, the system is going to respond to try to minimize that increase in pressure, and one way it can do that is by minimizing the number of moles of gas. So when I increase the pressure, I will see it will go to fewer moles of gas. For this system, that means going towards the reactants or towards the left. We have 1 mole of gas on the left side, and we have 2 moles of gas on the right. When I increase the volume, I'm going to see that it's going to shift to the right because I'm favoring the more moles of gas, because as I increase the volume, I decrease the pressure, and our system is going to try to compensate that by making more moles of gas. So we're going to favor, in this case, the right side, or favor the decomposition process. Decreasing volume is to the left, increasing to the right, and decreasing to the left. So when I look at my answer choices, what I'm looking for is which of these sets of changes are going to favor only the decomposition or only going to the right. And where I see that in is answer choice D. Removal of Cl2 favors the products, increasing the temperature, and increasing the volume. So D is our best answer.